Welcome to a new microeconomics video lesson in this block dedicated to game theory. In this video, we continue with that we learned about dynamic games and their basic elements by seeing how to solve this type of games. To do this, we will introduce the concept of subgame perfect equilibrium. The first way to solve dynamic games is using similar models than we have learned for static games, for example, using Nash equilibrium or dominant equilibrium. Although these concepts were defined for static games, they are still valid in dynamic games. Of course, one must take into account where strategy is in a dynamic game. As we know, here the strategy are a more complex concept than in static games. For example, finding the Nash equilibrium in the mini ultimatum game is very straightforward. It's enough to apply the golden rule described in previous videos. We can see that the best response for player 2 when player 1 is playing O1 will be both vectors A1, A2 and A1, R2. And when player 1 is playing O2, the best response for the opponent will be both vectors A1, A2 or R1, A2. And looking for columns, the best response for player 1 will be both playing O1 or A2 according to the responses of its opponent. There are three strategy vectors that can be equilibria here. The first one, O1, A1, A2. The second one, O1, A1, R2. And finally, the third one, O2, R1, A2. Let's use this to example to introduce a new concept. For this, let's consider the equilibrium, for example, O2, R1, A2. If we think about it, the reason why player 1 finds it optimal to play O2 in this equilibrium will be because they believe that player 2 would reject offer O1 if it were made. Is it reasonable to think this? Of course not, because in the hypothetical case that player 1 offered O1, player 2 would get more utility by accepting that by rejecting. In this sense, it is said that the strategy R1A2 of player 2 contains a non-credible threat, that of rejecting offer O1 if it were made. Notice that the same occurs with the equilibrium O1, A1, R2. It also contains a non-credible threat. In contrast, the equilibrium O1, A1, A2 doesn't contain any non-credible threats because all players behave optimally in every situation, even the hypothetical ones. Now it's time to define the concept of perfect subgame equilibrium. A Nash equilibrium is said to be subgame perfect if it contains no non-credible threats. This definition is intuitive but somewhat imprecise. For a more precise definition, we will use the concept of subgame. Recall that a subgame is a part of the game that, considered in isolation, has the form of a decision tree. A Nash equilibrium of a game will be a subgame perfect if it constitutes a Nash equilibrium in each of the subgames of the game. For example, in the mini ultimatum game there are two subgames, one for each node of player 2. The equilibrium O2-R1-A2 is not a subgame perfect because the player plays strategy R1 in the left subgame, and this is not an equilibrium in that subgame. Something similar happens with the equilibrium O1, A1, R2. In contrast, the equilibrium O1, A1, A2 does yield an Nash equilibrium in each subgame. Then how can we find subgame perfect equilibrium in a game? One possible way is to find all the Nash equilibria of the game and then analyze each subgame to see if those equilibria contain any non-credible threats, as we have just done in the previous slide. Another way is to use the method of backward induction. We can use it in any decision tree with a finite number of nodes, where players never make simultaneous decisions, for example in chess or in the mini ultimatum game. Note that it requires assuming that the rationality of the players is common knowledge. We will describe the method with an example. The first step is to consider one by one all the terminal nodes. That is, those where all actions or arrows point directly to a vector of payoffs. In the sample, there is only one, that of player 3. If the game reached this node, what would player 3 choose? Clearly, the action leading to the highest personal payoff, in this case, playing P3 and winning 5. Now we consider one by one all the penultimate nodes, that is, those whose arrows point directly to a terminal node, at least one of them, or to a vector of payoffs. In the example, there is only one, that of player 2. If the game reached this node, what would player 2 choose? Knowing that player 3 is rational, player 2 knows player 3 would choose P3 at the final node. Taking this into account, the best for 2 is to choose P2 and win at the final node 2. The only node left to consider is that of player 1. Since the rationality of the players is common knowledge, player 1 knows that player 2 and player 3 would choose respectively P2 and P3 if they had to act at their nodes. Taking this into account, the best for 1 will be to choose P1. With all this, we have obtained the strategy vector P1, P2, P3 as the perfect subgame equilibrium using backward induction. Thus, it can be shown that this strategy vector will be a subgame perfect equilibrium. Note that in longer games, the process must be continued until all nodes are considered. Always, however, working from the terminal nodes of the tree backward the initial node. Imagine how it would be in chess, for example. If some player is indifferent between two or more actions at the node because they yield the same payoff, then the game will have multiple perfect equilibria.